Hello there. As promised in last week's video, we take a look at another proof of assertion number 2 of our classification theorem for cyclic groups. Here it is. Assertion 2 states that for every divisor D of the group order n, where G is a cyclic group of order n, so the generator has order n, for every divisor D of n, there is a unique subgroup of this order. So in the case of cyclic groups, we have a converse statement of Lagrange's theorem, which holds. In last week's video, we did a rather abstract proof of this statement using the generalized correspondence principle. Here I'm going to walk you through a more concrete proof, which in itself I think is quite beneficial. So we do not use our knowledge of the subgroups of the integers, and we do not use the correspondence principle, but we're doing the following. So D is a divisor of n, so n divided by D is a natural number, so I can write down this here. X to this power clearly is an element of the group, and the subgroup generated by it, the cyclic subgroup generated by this guy, is a subgroup of the order of the generator. But by proposition 30, this is given by n divided by the greatest common divisor of n and this fraction here. But if D is a divisor of n, then so is n divided by D, simply because of this equation here, and this being a natural number. So the greatest common divisor is just this guy himself, n divided by D. So this simplifies to D. So this cyclic subgroup has exactly order D. So this proves that there is a subgroup of order D, and here we clearly see its generator. We also arrived at this result, but with a more abstract reasoning. So now to prove that this subgroup is unique, we have to put in a little bit more work. So we assume that we have a subgroup of G that is of order D, and then we have to prove that K actually is already this subgroup here. Okay, now there comes a very general statement. If I have a subgroup of a cyclic group, then it is of this form here. It is generated by x to the z, z being the smallest natural number such that x to the z lies in K. Natural numbers do not include 0, otherwise this would just be the identity, which clearly lies in K, but then this group generated by it would also be the trivial subgroup. Okay, first of all, I thought I omit this proof because the blackboard ended here, but this is still supposed to be a friendly introduction to abstract algebra, so we are indeed going to take a look at this proof. So this proof here will be complete. So, okay, let's prove this statement. This is essentially the same proof as it was on problem set number 5 for the integers. Of course it is, because this is a special case of this statement here, because the integers are cyclic and generated by, for example, the number 1. So the statement would be any subgroup is of the form 1 to the D, which we write as D times 1 because we are an additive group. So any subgroup of the integers is of this form, where D is the smallest natural number such that D times 1 lies in the subgroup. This is what we will prove here in a general setting and in multiplicative notation. But this is the only difference between the proof back then and this here. Okay, first of all, we observe we will find a natural number between 1 and n, again n being the order of x, such that x to the k lies in the subgroup capital K. X to the a, I hope I said. X to the a lies in capital K. For example, if a is equal to n, then x to the n by definition of the order is the identity, and this clearly lies in K because K is a subgroup. But then by the well-ordering principle of the natural numbers, if there is such a number, there is also a smallest such number. And this we call C. So C is the smallest natural number lying here, such that x to the z is an element of k here. And now our claim is that this here already generates k. So we prove that these two sets are the same. This inclusion follows easily because x to the z is an element of k, and then also the subgroup generated by this element must lie in k, because k is a subgroup, and this subgroup generated by this element is the smallest subgroup that contains x to the z. So this here is pretty clear. The other direction is harder. So we take any element, small k and capital K, and must show that it lies in here, so that it is the power of x to the z. Okay, now we know k is a subgroup of G, and G was generated by this element x. This means that this here can be written as x to the b for some number between 1 and n. I could have also written here 0 and n minus 1, that depends what you like more. Here I wrote 1 and n, x to the n being the identity, which would be the same as x to the 0. Okay, doesn't matter. And now we use the division algorithm. We can write this b here as q times c plus a remainder r. Q and r are natural numbers, or 0, and the remainder lies between 0 and c. This is important, and it is less than c. This is exactly what division with remainder means. So I can write r as b minus q times c, and x to the r then of course is this here. And now using the power laws that hold in any group, I can write this as x to the b times x to the minus qc, which is the same as x to the c to the minus qth power. But x to the b lies in k by definition of b. X to the c lies in k, this was our assumption, and because k is a subgroup, so does any power of x to the c, and again because k is a subgroup, any product of elements of k stays in k, so we see that this here lies in k, hence x to the r lies in k. Now comes the important argument. R is a natural number, or 0, that is less than c. But c was the smallest natural number such that x to the z lies in k. So r cannot be a natural number because it is less than c, so it must be 0. But if r is 0, this means that b is q times c. So this k that we started with is x to the b, which can be written as x to the q times c. By a power law, this is x to the c to the qth power, and this by definition lies in the cyclic subgroup generated by x to the z. So we end up that k lies in here, and this is what we wanted to prove. All right, as I've said, same idea as for the integers, only in different notation, and the important argument here is using the division algorithm. Okay, now that we have proven this, we are almost done. First of all, we observe that this fraction here, which is clearly d, is the order of k. But by definition here and proposition 30, we know that the order of this cyclic subgroup is exactly the order of the generator, which again by proposition 30 is this fraction here. So now if I compare these two, I end up with the greatest common divisor of n and z must be the n divided by d. So, but if it is the greatest common divisor, in particular it is a divisor of both n and z, so n divided by d is a divisor of c. But that means that x to the z is an element of this subgroup here, because you can write z as some integer times n divided by d, and this exactly means that this here lies in this cyclic subgroup. As always, if you're a beginner and this statement that I just spoke out without writing it down was not clear to you, please pause the video and think about that again. write this here as C being, I don't know, K times N over D. And then you will see that X to the Z is actually an element of this cyclic subgroup here. So we can conclude that K, which was this here, must be a subgroup of this. Because if this element lies here, then the group generated by it, which is the smallest subgroup that contains this element, must also lie in this group here, because this already is a group. But the order of this here is D. We just saw that. The order of D is exactly the order of K. So K is a subgroup of this group with the same order. But that only leaves us with this possibility that K is already this here, and we have shown uniqueness. So if I have any subgroup of order D, then it already must be the subgroup generated by X to the N over D. All right, this is more concrete, I think, but also clearly not a trivial proof and not easy for a beginner to understand every step, I think. All right, that's it for the classification of cyclic groups, our first big classification theorem, which involves a lot of theory, I think. Very neat proofs. In next week's video, we are going to talk about generators of cyclic groups, and we will write down the automorphism group of a cyclic group explicitly. All right, thanks for watching. Bye-bye.